All right, howdy everyone. We'll get started. So welcome. Thanks for coming a little early today. I figured I would try and give you a couple extra minutes to answer your questions before the exam on Friday. I'm assuming that's why you're all here. But for that, your exam is Friday during class time. You just have to show up to, like, if you're having a regular class, you're just going to take a test instead of getting lectured. There should be a seating chart up if it's not up already soon. And then it's just during class. It's all multiple choice. It's on paper. And you'll turn it in at the end of class. Are there any questions about the exam? How do you feel about it? Okay, so let's turn those upside downs into gigs. Okay, so where do we want to start? What questions do we have? You can ask me anything from homework, practice, the exam, general questions. No, in the group me, there was a question about question 2 on the mock exam. Do you want to go over that one? Alrighty, so for question 2. For question 2, we have prochrane hydrochloride, excuse me, is used as a local anesthetic, and we want to calculate the molarity of a 4.612 molar solution, which has a density of 1.1066 grams per milliliter, and we're going to assume 1 kilogram of solvent. Okay, so there's a couple things going on here. Anyone know where to start with this?
Right.
Mass of what?
The protein hydrochloride.
Yep, and so what is that in this question? What are we going to classify that as? Perfect, right? So this is going to be our solute. Right, and we know that we have 1 kilogram of solvent. We are given 4.612 molal solution of this solution that we have. What are the units of molality? Perfect. So we have moles solute over kilograms solvent. So what can we get from this? I guess before you answer that, we want to get to molarity. What are the units of molarity? Mole over liters, and mole of what over liters of what? Perfect. So this is moles solute over liters solution. Okay. So what we notice when we compare molality to molarity is that we have moles of solute in both of these here, right? If we know the moles of solute, we can use that directly for the moles of solute in our molarity. So how can we get to moles of solute? Yep. And we're going to say that 4.612, right, moles solute over kilograms solvent is equal to X over what? Yep, we're going to say 1 kilogram, right? We have 1 kilogram of solvent from our question. So you can say 1 kilogram solvent. So what does that mean for moles of solute? It's that 4.612. Yep, so X is equal to 4.612 moles of solute. All right, so then how do we get to liters of solution? Yep, and how are we going to use density? Yep, we need the molar mass. So how are we going to use our molar mass? Multiply which number? Yep, perfect. So our moles of solute, right, is that procaine hydrochloride. So in order to get to grams of that, we need to use its molar mass. So we're going to use 4.612 moles. And we're going to use its molar mass of 1 mole over 272.77 grams. This is 1258 grams of solute. What can we do with that?
Like the density, to figure out how many kilograms you have, strictly speaking of the solute.
Yep. Is there something else we can do too? We need to add 1,000, right? So when we talk about the density of the solution, it's for the solution. The density is the solution. The solution contains both the solute and the solvent. So we're going to include 1.258 kilograms plus 1 to get 2.258 kilograms. Right, or you can add 1,000 if you want to do grams and kilograms. So in order to get to milliliters, or in order to get to liters, right, you're going to go back and forth between 1,000 a lot. We can have 2,258 grams equal to 1 over X, because we don't know our milliliters, over 1.1066 gram per mil. We end up with 2,040 milliliters, which is 2.04 liters. And what is that the liters for? Liters of the solution. And so now we have our moles of solute, which matches our moles of solute for molarity. And we have our liters of solution, which matches our liters of solution for molarity. So what's the last thing we need to do? We need to take our moles of solute divided by our liters of solution. And we end up with 2.26 mole. Which is A. Okay, what questions do we have about question 2? Does everyone understand the roadmap of what we used? Right, we started off with molality in moles of solute over kilograms of solution over solvent, excuse me. We used our density to get from solute to solution. All right, solvent to solution, combining our solute and solvent mass in order to get the mass of the solution. And then we used the moles of the solvent that we found from our molality, and then the liters of the solution that we found using our density to get to molarity. Does that clear up this question? Yes, okay. What else do we want to see?
Could you, I don't know if you can use that, but number 6 in the quiz.
On the quiz, yes, I think I'm allowed to talk about that now. You might have a slightly different one on your actual quiz, I think, but for in terms of numbers. Right, this is one. Okay, which one do you have?
It's the one that's like the A to B one. A with next to-
Okay, I see that one. It's a different number. For me, sorry. We can do this one and we'll come back to that one. Yep. This is kind of good for what we just did. All right, so we have calculate the molarity M of NH3 in household ammonia solutions, which are 8.56% aqueous solutions by mass. We know the density of the solution is 0.965 grams per milliliter, and we're given our molar masses. Okay, so kind of similar to what we just did, but a little different. How are we going to go about this one? What can we assume when it's percentage by mass? Right, so we can say that it's out of 100. So if we have 8.56% aqueous solution, that means we have how many grams of ammonia? 8.56. And how many grams of water? Divided by 100, right? When it's by mass, we're saying that out of, right, a percentage. So out of 100 grams, 8.56%. Yeah. The solution or so like, yes, you're correct. It's the solution. But we know that aqueous is water. So I'm just to differentiate between the two. I just put water, but it would be that, right? The ammonia dissolved in the water. Okay. So this is, right, this is what your density, right? That solution is 100 grams, and that density is where that comes from, is the solution. All right. So if we know that we have 8.56 grams of ammonia, we're looking for molarity, which we said is moles over liter. So how are we going to get from grams to moles? Molar mass. Okay. And then what is our solution? What's the mass of ours? Yep. So then we're going to say that, right, in order to get to liters of solution, we're going to have 100 grams. We're going to use our density. So 0.965 grams over 1 milliliter. The correct dimensional analysis. Right, so we have 100 grams. We have X amount of mils, right? And our solution is 0.965 divided by 1 milliliter. So this will end up with 103.6 milliliters, which goes to 0.1036 liters. And then we can take our moles and our liters and get our molarity. Four point eight five. Okay, does this make sense for that question? Any other questions on this one for the mass? Do we see how it's kind of similar to the one from the mock exam, right? It's just slightly different unit we're starting with. Awesome. Okay. Right, this is the one you're looking for. Right, so the next one is from your quiz as well. So we have I paraphrased a little bit just so I didn't have to write everything down. But we have a solution of an unknown polar compound K is mixed with water, and we want to consider the four states of the system. So state A is pure K and pure water before mixing, right? So you have a solution of K and you have a solution of the pure water. State B is separated K, right? So we have the pure water here, and then we separated K and broke its IMFs. State C is that you've already broken K, and now you're breaking your water IMFs. And state D is when that solution forms. Okay. We said that the boiling point of pure K is 58 degrees Celsius. So which transition state requires more heat? Right, you have to choose which state. And which one, so which one's gonna require, and then we said. Okay, so we said which we want, or we asked, what is the transition that requires the most heat? So A to B, B to C, or C to D. Why do you say A to B? Which one has a higher boiling point? Than what? What is the boiling point of water? 100 degrees Celsius, right? So the thing to note here is that water boils at 100, right? It freezes at 0, boils at 100. So which one has the higher boiling point? Water has the higher boiling point. So which transition is going to require more heat? The water one. So B to C is going to require the more heat of this situation. Right, so B to C requires more heat. Do you see why that does that make sense why that's happening? Right, if you were to heat both of them on the stove at the same time, K is going to reach its boiling point faster, right? They're both starting at room temp, about 25. It's going to reach 58 before it reaches 100. So it's going to require more heat to break all of those IMFs in the water than it is to reach that K. Okay. So the second part of the question is, upon mixing, the solution feels warm to the touch. Draw an enthalpy diagram like the one shown in class. Which transition between states requires or produces more heat? Consider the magnitude of the transition and choose from the drop-down menu, right? So which one is going to if your solution is feeling warm, which transition requires or produces more heat? Which is which step?
I think. But I think it's something to be.
Yep. So delta H of hydration is when, right, we're mixing those compounds. So that's that transition from C to D when we're actually mixing the compounds. Since it's hotter, does that mean we are releasing or absorbing heat? We're releasing that heat, right? So the solution is getting warmed up, we're releasing heat. So this transition state releases more heat. And this is your delta H of hydration.
The delta H of hydration is bigger than the delta H of the lattice?
Yes.
Okay.
Yep.
What's delta H of lattice again?
Delta H of the lattice is that energy to break your compound. So that polar compound that's being dissolved,
The solute?
the solute, yep. Usually it's an ionic compound, and so that lattice energy is the energy between the charged particles. So the lattice energy is what it takes to break that bond. And since we're ending up with a positive heat, that means that heat's being released at the very end, showing that the hydration's more, showing that it's an exothermic reaction. So that means that the delta H of the hydration is bigger than the delta H of the lattice. If it was colder, the lattice and breaking that energy would require more than what the delta H of the hydration is. Does that make sense? Does that help that question on your quiz? Okay. What other questions do we have? Does this one make sense for everyone? Why those transition states are the way that they are? Okay. Do you have a question? Yes. Yes. Yep. So if we're looking at, right, an ionic compound, if we look at NaCl, for instance, right, this is a metal and a non-metal. What are electrons doing here? Are they sharing or transferring? They're transferring, right? It's ionic, so electrons transfer. When we look at a covalent compound, right, if we look at HO, we draw that bond between them because they're sharing that electron. However, your bond is so strong in NaCl that electron flips from the sodium to the chloride. So in order to break that bond, in order to remove those two atoms away from each other, you need to require energy. And all bond breakage requires energy. So that's going to be a positive delta H, where now we have separated things, there's no energy around them. We're going to form the bonds when it all mixes, right? It's going to form between sodium and the water molecule, right? This is going to form a bond technically. So that bond forming, those IMFs forming, is the negative delta H. What other questions?
Question.
Practice. Yep. Yeah, great transition. Right, so for question 9, we said that an unknown ionic compound MX dissolves in water and the solution feels cool to the touch. Which of the following pairs of inequalities is correct for this process? Right, so think back to our quiz question we just did. It was warm to the touch. Now this one is cool to the touch. So which one do we know is going to require or release more energy here? Which one's stronger, the lattice or the hydration? The lattice, right? The lattice has to require energy. It has to take energy in from the system. Once we dissolve everything, there's not enough energy that's released in order to make the system warm, right? It remains cool. So the lattice breakage requires more energy here. Right, and we know that because the solution feels cool to the touch. Yes, so it's an endothermic. Yep. So We know that delta H, B, and D we can get rid of because delta H of the lattice has to be bigger than delta H of hydration. And what do we know about this portion here? What's different here? Right, which one's greater is either the delta H of the solution or the delta S of the solution. And what happens, which one's going to be correct and why? Delta S. Yes, and why is it greater? Perfect, right? So we know that we're taking an unknown compound and we're dissolving it in water. When we're making that solution, we're adding more entropy to the system, right? So entropy of a solution is always going to be greater than entropy of a pure solvent. Putting stuff in solution will always increase entropy. So your delta S of the solution is going to be greater. It's going to be C. Mhm. Yes. Yes. It's mostly just the solute, but water also needs to be broken. Yes. Yep. Yep. Right. And you're just forming a solution. And so that's always going to increase your entropy. That's always going to be bigger than the rest. Yeah.
Is the delta of lattice always greater than the delta of hydration?
No. Nope. So when your solution feels cool to the touch, that's because your delta H of the lattice is bigger than the delta H of the hydration. If your solution was warm, then your delta H of the solution is bigger.
Making a solution delta is the solution always greater than delta.
Yes. And along that line, right, forming a solution, your delta S of the pure solvent is always less than the delta S of the solution. Right, in case she asks a similar question but changes what's on the outside.
So if the hydration entropy was greater, the solution would be exothermic.
Yes. Yep. Right, and so since this is feeling cool, we are absorbing energy. So this is an endothermic reaction. Where warm would be exothermic because we're releasing heat.
If it is an exothermic solution, the delta S will be bigger.
Yes. Mhm. What other questions? Yep. All right, so for number 8, we have 2 aqueous, I'm going to guess solutions is supposed to be there. 2 aqueous solutions are prepared. We have a 1 molal sodium carbonate and a 1 molal sodium chloride at room temperature. Which of the following statements is true, assuming 100% dissociation? What do we need to know for this question? Yep, we need to know the Van Hoff factor. So the first thing I would do, I was write out my dissociation. Sodium carbonate. What does that do? 3, because why?
Because the sodium is associated with ions and CO2.
Perfect. So this gets a Van Hoff factor of 3. And then what does lithium chloride do? This is 2. Okay, and now we're asking for osmotic pressure. What is the formula for osmotic pressure? Perfect. That is given to you on your formula sheet. You don't need to memorize that one. But you do need to recognize that it's osmotic pressure. It's not labeled as osmotic pressure. Okay. So looking at these, right, what's changing between our two compounds that are dissolving? What's the only thing that's different between them? The Van Hoff factor is really the only thing that's different, right? We have 3 ions in our sodium carbonate, and we have 2 ions in our lithium chloride. So if we look at A, we say that the sodium carbonate solution has a higher osmotic pressure and a higher vapor pressure than the lithium chloride solution. What does this mean? What does osmotic pressure mean?
Or is more pressure to get it to not with the semi-permeable membrane, right?
Right. So when we're talking about osmotic pressure, that's the osmosis. We're trying to dissolve. We're trying to flow from something with high concentration, something with low concentration to high concentration, right? We're trying to dilute the high concentration stuff. So, right, we're going to have a higher concentrated solution with our sodium carbonate. So the higher osmotic pressure is correct because we have more ions in solution. So it's going to have a higher osmotic pressure because more stuff needs to flow into that higher concentrated ions in order to dilute that solution. That makes sense why higher pressure is, or higher osmotic pressure. Right, there's more ions, those need to be diluted. Yep.
Don't they have the same molality? Or am I looking at the wrong?
They do have the same molality. However, for osmotic pressure, we still have this I component, and that's the Van Hoff factor. So since there's 3 ions for the sodium carbonate and only 2 for the lithium chloride, there's just more stuff in the solution when that all dissociates. Yep. So then along the same lines, now we're looking at vapor pressure. What is vapor pressure?
The gas above the solution.
Good. Vapor pressure is the pressure of the gas above the solution. Is it easier for a pure solvent or a solution? Or I guess which one will have a higher vapor pressure, the pure solvent or the solution?
Pure solvent.
The pure solvent will always have the higher vapor pressure. Why is that?
Does the ions get in the way of?
Perfect, right? When we have a solution, right? If we just have a pure solvent, these can go back and forth no matter what. Think about what's on the surface. There's only that solvent that's on the surface to reach and go in between gaseous and liquid phase. However, when we have something dissolved in it, now sometimes we're going to have those solute particles that are now at the surface. So instead of 100% of that solvent being on the surface, now we have some competing particles in order to reach that transition between the gaseous and liquid phase. So the more things that are in solution, the more that things that are competing to reach the gaseous phase. So which one has more things in solution? The sodium carbonate or the lithium chloride? Sodium carbonate has more things in solution, so that mean higher or lower vapor pressure. That means lower vapor pressure, right? More things means lower vapor pressure. So B is going to be your correct answer here. right? This cannot be true because this is a lower vapor pressure. And then to prove that lower freezing point is correct, right? This is we still have that I component for the freezing temperature. And again, if we think about vapor pressure, we think about things escaping to the gaseous phase. Now, if we're trying to freeze it, the more things in solution, the more things that are in the way before those molecules can freeze together, right? They have to move around those ions in solution in order to freeze. So that's going to lower its vapor or lower its freezing point more than the thing that has less stuff. Okay, does that make sense why we're proving that B is correct with the freezing point? Right, so if you're making pasta water and trying to boil it, the more salt you add in, technically the higher your boiling point needs to get. And the more salt you put on the road, the lower the freezing point has to be. Does that help answer your question with E? What other questions do we have? Right, so for number 11, we have considered the following chemical reactions of the system and its associated thermodynamic data carried out under constant pressure and standard state conditions. Right, so we're given that the substance is POCl3, and that's breaking down into PCl and O2 gas. We're given the delta H and the delta S. And we're saying that assuming delta H and delta S do not vary with temperature, select the correct plot of delta G in kilojoules per mole versus T in Kelvin for this process. The y-intercept, x-intercept, and slope must all be correct, and note that delta G axis scales of the graphs are not all the same. Okay, so what is this asking for? All of those words to ask what? Yep.
We have to start with like finding out.
Great, right? Perfect, right? So we need to find the delta H and the delta S, right? At the end of the day, they're asking about G. What does G tell us about a reaction? That gives free energy, and that tells us if it's blank or not blank. Spontaneous or not spontaneous. So really what this question is asking is, when is this reaction spontaneous? Right? That's what it's asking for. And how do we solve that is if we know what delta G is. So we need to find what the delta H and delta S for this reaction is. And this is just going to be the standard state. So we can do products minus reactants. So delta H naught is going to be okay. So I got delta H to be 554.8 kilojoules per mole. Is this an endo or exothermic reaction? This is an endothermic reaction. What does the world prefer, endo or exo? the world prefers an exothermic reaction. So, right, ideal conditions for a spontaneous reaction is an exothermic reaction and something that increases entropy. So, are we going to be struggling to get this reaction spontaneous? Yes, right. Automatically, we know that it's not always going to be spontaneous because it's not an exothermic reaction. Okay, so that should be key number 1 in your head. Then we need to solve for delta S, and that's the same thing. Then I got delta S equal to 195 joules over mole Kelvin. So is this increasing or decreasing entropy? This is increasing entropy. Does that match our reaction if we were just to predict it based off of the reaction? Right, if I didn't give you any numbers and I asked what's going to happen to entropy for your reaction, what would you guess? It would increase. Why is it going to increase? Not for that reason.
Right.
Perfect, right? So for one, we go from 1 product to 2 products, right? We go from 2 moles of something to 3 moles of something. So that's increasing in entropy. And what we're increasing in is producing gas. And that's going to be our most entropic thing. So if we produce gas, it's already increasing entropy there. So we are predicting this increasing entropy. Our numbers support that we're increasing entropy. So that's good there. Okay. So now that we know what delta H and delta S are, we can look at our graphs at the bottom. So for graph B here, they're showing that delta G is always positive. In what conditions would delta G always be positive? For delta H and delta S. Perfect, right? So it's always going to be positive, or delta G will always be positive when delta H is positive and delta S is negative. Is that our case here? No. So we could automatically get rid of B because we know that at some point this will be spontaneous. Is there another one that we can get rid of? Which one? We can get rid of D, right? We said that at some point this is not going to be spontaneous because we know that delta H is positive. So at some point there's going to be a crossover where the delta H or the delta S is going to take over. Okay. What's the equation we're going to use for this? What's the big delta G equation?
Delta H minus E delta F.
Beautiful. Right, so these are this is also given to you on your formula sheet. So if we have a positive delta H and a positive delta S, when is this going to be spontaneous? At high temperatures, right? So this is going to be spontaneous at high temps. So looking at A and C, where is our delta G negative at high temperatures? A, right? At negative delta G, we have high temperatures. So A is going to be our correct answer. We don't even really need to solve for T because we know that's only going to be spontaneous at high temperatures. And so once we get into that high temperature range of our x-axis, we see that we're in the negative range of delta G, showing that it's spontaneous. How would you solve for what temperature it would be spontaneous at? Perfect, right? We know that when it becomes spontaneous, delta G is 0, which means that delta H is equal to T delta S. So T is equal to delta H over delta S. And you can solve for T in Kelvin there. And you can confirm at what temperature that is crossing over. What do you have to do about delta H and delta S if you solve for T? Yep, we have to make sure that our units are the same, right? Here we have kilojoules per mole, and here we have joules per mole Kelvin. So just make sure that either both of them are in kilojoules or both of them are in joules. Who asked for 11? Does that help? Does that help 11? Any other questions with 11? Yeah. Oh, sorry. There's something I was going to say about this. Right, so before you even do any math, I always like to ask myself what I predict the answer to be, right? Kind of make sure I'm checking along the way, right? Ask yourself, does this make sense? Right, does your positive delta S make sense? Looking at your equations, can I predict when it's going to be, prediction is going to be spontaneous even before I solve that question? And then I could always go back if I had time to solve and check my answer to solve for T. But you don't necessarily have to complete the question in order to get the right answer. Why is C wrong? D, yep, so if you look at the axis for D, they're all negative numbers. It is always negative. So in this case, there's never a time where delta G is positive, and delta G is positive when it's non-spontaneous. We know that since we have a positive delta H and a positive delta S, at some point, at some time, we will have a non-spontaneous reaction. And so at some point, it has to show that it's not spontaneous.
If you have like a linear equation, it always work out where like if you rearrange it, you can just plug in like to the delta H minus T delta S, where it's like the same. Like if you plug it in, like the numbers are the same. X is the temperature.
Yep. So this is Y equals B plus, right, MX plus B. Right, that's what that is. So if you're in this form, then delta G naught is equal to negative T delta S plus delta H. Right, you can rearrange it and that becomes Y equals MX plus B form. So all of those equations that you see in your plots, you can also plug your numbers into those and see if you get the correct answer there as a second form of checking. Does that answer your question? Any other questions with 11? Okay. Your question? Yeah. Mhm. Okay. So we have, which of the following pairs is likely to have the highest solubility of solute in solvent at a certain temperature? Consider the intermolecular forces in solute and solvent before mixing and the intermolecular forces after mixing. Alrighty, so for this question, right, we're looking at solute and solvents. They're always doing solute in solvent from left to right. And we're looking at our intermolecular forces between them. So what do we know about dissolving? What is our little term? Yep. Likes, dissolve, likes. So we want the highest solubility. So what do we want? Necessarily, right? We just want something that's polar dissolving something polar or something non-polar dissolving something non-polar, right? We want those likes to dissolve each other. When we look at influences between chain size and like the size of the molecule contributing to its boiling point, as long as they're all within about 30 or so grams per mole, then you can say that those are negligible and you can just look at the main intermolecular force that we're seeing. All right, and all of these here are about the same molecular weight, so you don't have to worry about like size being the factor here. We can just kind of focus on those intermolecular forces first. Okay, so when we look at methanol, is this going to be a polar or non-polar compound? This is polar. And what about hexane? What about hexane? That's non-polar, right? Oh, it says hexane. Right, we have one butanol. And what is that, polar or non-polar? It's like bordering polar, non-polar. I would say it's like a little polar. Wait, we're gonna say this is a little polar. In what? What's H2O? Polar. We have diethyl ether, which is, that's pretty non-polar. In water, polar. And then we have one butanol in hexane. So what is this one? This one butanol we said was like a little polar. In hexane, which we said was non-polar. Okay. So any of them that we can get rid of either way. Yep, so A and C, we have a polar and a non-polar, and then a polar and a non-polar, and then a non-polar and a polar, right? So those are going to be kind of sad. But then we have a little polar in a polar molecule, and then a little polar in a non-polar molecule. So this is when we start looking at the size, right? Once we have to start focusing down to between polarity and non-polarity, we're just saying that, right, one butanol is a pretty big molecule. It has that little OH at the very end, but it's not going to contribute too much to it for that because we have all of this non-polar side chain right next to it. In something that's really, really polar, right? H2O is very polar. However, when we look at D, we see that we have something that's a little bit polar because of that OH, but mostly non-polar in something in a very non-polar substance. So which one's closer to likes dissolves likes? D is going to be closer to likes dissolves likes. Right, we also have molecules that are of similar size. Those one butanol and that hexane are looking pretty similar to each other. That's going to be pretty easy to dissolve each other as well. Yep.
Can you show us the harder version of this question?
Potentially. I'll look for one and try and come up with it. Yeah.
When I was doing the Alex for like that, this question specifically, they would consider the OHs and the O. And so it would match them with both
Yes.
on the Alex.
Okay. So yes, and like that's true. Can one butanol be dissolved in water 100%? Right? That OH molecule has hydrogen bonding that will hydrogen bond with water and be a polar substance. But it over, I think, 3 CHs in a row. So like you can have CH3OH and then CH3, CH2OH and CH3. those three are all, these are all polar. And that's because that OH is contributing so much that it doesn't offset the carbon chain. Once we get to that 4, then the carbon chain is more important than that OH. So with the diethyl ether, right, we have 4 carbons total and an oxygen. And that is, this is, looks like this. So it is a symmetrical molecule contributing to non-polarness of it. It's still bent, so it has a little bit whatever, blah, 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 but it doesn't hydrogen bond. So it's a little bit less polar than the butanol. So once we get into that 4 carbon chain, that's when it starts contributing more non-polar than polar. Sorry, that was a big like explanation to do, but. So if you see 3 or less, pair it up with a polar something. If it's 4 or more, you can pair it up with a non-polar. And that might be what the Alex is doing. I don't remember all the questions too much. Any other questions on the dissolving? I forgot. I don't really know if there's a harder question than this that she would ask. Yeah.
I was just gonna say, like, could you look over that Alex I'm doing?
Yeah, is it like an old question?
So-
Yeah.
These better questions.
Mm. Okay. We'll do this one just first, right? So we have this nitrogen oxygen compound. And then we're either going to put it in some nitrogen with a carbon chain compound, right? It's going to look like that. Or we have your ketone. Okay. What do we know? What do we think the thing on the solute is? Is that polar or non-polar? This is polar, right? If we look at our differences in electronegativity, this is going to have our dipoles. That's going to be non-polar, right? It's not symmetrical because we still have that oxygen double bond. What do we think that nitrogen in the carbon chains, what is that going to be? That's probably a little polar, pretty non-polar, right? If we count up all the carbons, we have 6 carbons total. So we're in that 4 plus. So this would be like our non-polar option. And what about the CH3C? That one. That one would be pretty polar. So which one is the nitrogen going to most likely dissolve in? The bottom one, right? So this is gonna be the nice one there. Does that make sense? Yeah. I'm doing the same thing in my head. I'm just. I shorthanded that. So we have this NH4Br, and that's either gonna go in ethanol or some benzene molecule. So what is NH4Br? Polar. Why is it polar? Because what is this? This is an ionic compound, right? Ionic compounds are very, very polar, right? So this is ionic, this is polar. Which one is it going to dissolve in? The top one, right? Because we're 3 or less. So this one's going to be pretty polar. This benzene ring is very nonpolar. So your ionic compound is going to have a much easier time dissolving in the ethanol than the benzene ring. Yep.
Could you re-explain how it's an ion? only?
Yep. So what is bromine? What charge does that have? So bromine's going to have a -1 because it is a nonmetal. And what is NH4?
Plus-
This is +1, right? This is the ammonium polyatomic ion, so this is going to be NH4 plus. Since we have full charges on the NH4 plus and the Br minus, those charges is because of a transfer of electrons. And so this is going to be an ionic compound, and ionic compounds are so polar, right? They're no longer sharing, they're transferring electrons. Okay, and then if y'all are writing these down, if you have to go on to take Orgo, you're going to come back to these notes and say, oh my God, it's so much easier to write now. It's kind of breaking my brain to look at. Okay. So what about our solute here? So it's going to be polar or non-polar? Yeah, this is about 4 or more, but how many oxygens do we have here? We have a lot. So, right, we can look at 4 or more when we only have 1 oxygen, but this time we have 1, 2, 3, 4, 5, and then this one over here, 6. So all of those are going to contribute to it being a very polar molecule. I would consider this one polar. So which one is it going to be dissolved in? The top one. Yep. This methanol here is pretty polar. If you look at this bottom one here, if you fold it in half, that's symmetrical. So that's going to be nonpolar. So I would guess that this big molecule dissolves in the methanol first. That's a naming thing. So when we look at 1-butanol, you can label this as 1, 2, 3, 4. So it's just telling you that the OH is on that first carbon, right? If it was 2-butanol, then it would be coming off of this one instead. This would still be a little polar here. The OH being on the end makes it more polar than the OH being in the middle. Great question. What other questions do we have? Sure. Let me read through it and find it. Okay. So you have an aquarium of fish that deal. Okay, so the second portion of this question is asking, do you need to change the temperature of water in order to increase oxygen levels? So, right, either yes, you do, or no, you don't. So what happens? So does anyone know, right, if you have to increase or decrease, right? What, if you increase temperature, what happens to solubility? Does it go up or down? Down, right? So if we're taking something that's a liquid, right, and we are going to increase temperature, does it become more gas-like or more solid-like? If we increase temperature, more gas-like, right? So instead of, right, I'm gonna kind of fudge it, right? Instead of it being a surface, now we have, right, more space. We're gonna call it up here, right? So there's more space and their particles are farther apart. Right? Instead of particles being like this, now they're like that, right? They're more spread apart. Therefore, it's harder to dissolve things in things that are more far apart because you can't create those IMFs, right? Dissolving is all about creating those IMFs between different molecules. If they're far apart, we're not having the same interaction, right? We say gases, they have no IMFs because they're filling the space of the room. So the more gas-like you have, the less IMFs you have. If we decrease temperature, now we go to a solution where our particles are really, really close together. Now we have really, really strong IMFs, so those solubility will increase because we can put more things in those pockets that are forming. So decreasing temperature always increases your solubility. So if you want to dissolve more, you bring the temperature down. Yes, I think so. It's like that colloid chart in your slides. I think it applies. I would have to look at the slides again to confirm that, but yes, so it's like, so I think it's the gases is what this is applying to in solutions, but then the liquids and solids, that's slightly different. Yeah. And I know I was just looking at the slide, there's some chart that gives it to you. Just look at that one more time. I just haven't looked at that in a second. Yep. Mm-hmm. Did that help answer your question? I forgot who asked that. Did that help? Okay, so use the thermodynamic data below for the given reaction to determine the temperature range at which the reaction is spontaneous. Okay, so this is very similar to the chart question we did. So we're looking here, we have delta H and we have delta S. So what they're asking for, right, is when is this reaction spontaneous? So what do we need to know? Or we need to solve for first? Yep, we're ultimately looking for, right, delta G, is it spontaneous or not? We're given the breakdown of delta H and delta S. Can we solve for those? Yeah, right, we can do the delta H of formation and delta S of formation. So delta H, right, is products minus reactants. Is this balanced? So then we have okay, right, so we have delta H is plus 41.2 kilojoules per mole. So again, we're in that same situation where we have a positive delta H which means that it's an endothermic reaction. It's not favorable by the universe, or it's not preferred by the universe. So is it always going to be spontaneous? No. So I have to find delta S. Right, and so we have the delta S is increasing in entropy. So will this be spontaneous at some point? Yes. So which one can we get rid of? We can get rid of C and D. Right? If this was a negative delta S, then we know that's going to never be spontaneous. But because it is a positive delta S, we know that it's going to be spontaneous at some point. Is it going to be spontaneous at high or low temps? High temps. So which one's your answer? B is your answer. Yep. And how could you prove that? Yep. We can see that delta H over delta S. So we would say 41,200 over 42.1. And this gets 978.6. So that checks off. Does that help?
The last one.
16? Okay. Okay, so we have, what is the entropy change in the system when 1 mole of water vaporizes at 100 degrees Celsius and a pressure of 1 atmosphere? Does anyone know how to solve this one? Yep, so we are using the delta G equation again. But we're saying that water is vaporizing. What does that mean? Where are we? We're at equilibrium, right? All phase changes are going to be at equilibrium. If you remember to your phase diagrams, heating curves, these here, right? This is your H fusion, and this is your delta H vaporization. We're on that straight line. Straight lines are always equilibrium. Those are phase changes. So if we're at a phase change and we're at equilibrium, what does that mean about delta G? 0. So if 0 is equal to delta H minus T delta S, then T delta S is equal to delta H. So that means that T is equal to delta H over delta S, which is what we've been using, right? That's where this comes from. So we can plug in 100 degrees Celsius, which is what in Kelvin? Yep, 373 Kelvin is equal to 40700 joules divided by X. And I got 109.1. joules per C. That help that. It would be the same thing. Yep. So it would be a different delta H for that one, because your delta H's are different depending on if it's freezing or boiling. But you would be the same setup. You would just be using a different delta H, so you'd have a different temperature, and you would just plug in 0 degrees Celsius, so then it would be 273 for your Kelvin. And then they might give you a different sample, right? So maybe it boils at 58 degrees Celsius, right? So it would be the same thing, just changing the temperature here. What other questions do we have? Are we feeling better? Yeah, okay. Yep. 6. Okay. Diethyl ether has a vapor pressure of 400 torr at 18 degrees Celsius. When a sample of benzoic acid, a non-volatile non-electrolyte, is dissolved in ether, the vapor pressure of the solution is 342 torr. What is the mole fraction of benzoic acid in the solution? Does anyone know how to do this one? Right, so P solution is equal to the mole fraction of the solvent times the pressure of the pure solvent. Okay, so what are we given? Are we given pressure? What are we given pressures of? Of the solution. Which one's the solution? 342. This one is solution. What else are we given the pressure of? Diethyl ether of the pure solvent. So this is PPS is what I'm going to call it. So can we solve for the mole fraction of the solvent? Yes. Right. So the pressure of the solution is always going to be less than the pressure of the pure solvent. So we have 342 is equal to the mole fraction times PPS, which is, we said was 400. So the mole fraction of the solvent is 0.855. Is that our answer? What's our answer? 1 minus this, right? We're asked for the benzoic acid. The benzoic acid is your solute. It's what's getting dissolved. It's saying that it is a non-volatile non-electrolyte, meaning that it has a Van Hoff factor of 1. So it's just 1 minus 0.855, which is C. Yep. Yes. So if you're given something that does dissociate, that's where, like that one clicker question she made a clarification of, right, your solvent is now going to look different. So your mole fraction is at moles solvent over moles total, and moles total would be moles solvent plus 2 times whatever that is, right? If you had an ionic compound that broke into 2, say. It gets a little tricky. There's a little bit more math that gets involved. It wouldn't be this straightforward of a question, and you would be given more information about the number of moles in solution in this case. Most of the time, she's probably going to ask about a non-volatile non-electrolyte just because it's 1, and it's good to go that way. Yeah, more straightforward. if it were something that had more than one Van Hoff factor, be on the lookout for moles, like you would be given the moles of that solute that's being dissolved, or you would be given the molarity of it and be able to solve for the moles based off of volume, right? You multiply the number of moles of that solute, right? So if you had 2 moles of NaCl, this breaks up into Na plus and Cl minus. This is all 1 to 1 to 1. So if you have 2 moles of NaCl, that means you have 2 moles of Na and you have 2 moles of Cl. So that means you actually have 4 moles total of your ions. And that's what's contributing to the mole fraction portion. Yes, if you were solving for the solute, it would be 4 over solvent plus 4. Yep, yes. That's a pretty complicated question. I would be surprised if she did something like that. The non-electrolyte is more probably upper speed. And if you do see that, I apologize, and I'll apologize for that. The next one is. Any other questions? There's like 2 minutes. I guess this is probably a good spot to end. So we'll end this for tonight. I did make the announcement about a Zoom review session tomorrow for y'all. That's at 7:30 p.m. assuming I'm able to leave lab by 7. So I will post that link tomorrow. Again, just come and ask any last minute questions you have. That will also be recorded and posted. If you just want to listen to that like a podcast on the way to class on Friday, that's fine. I'm not here next week. I'm out of town next week, so there's no review session next week. You will still have, I'll still post like all of the review sessions or review problems and stuff. But no review session next week, and I will see you on Friday. I think that's it. Yeah, thanks so much. If you have any questions, feel free to email me or come up to talk to me. And thank you for coming. And good luck if I don't see you beforehand.